This section is called Arc Length and Curvature, but we're not going to jump directly into learning about arc length and curvature just yet. In this section, we're going to continue dealing with vector-valued functions and the curves they generate. Now, as we've learned, there's actually a lot of ways that we could represent a vector-valued function that traces out a particular curve, right? We could trace out the same curve if we go fast, or if we go slow, maybe we could go backward along the same curve. There are lots of parameterizations that trace out the same curve. What we want to do in this section, a lot of what we want to do in this section, is think about what all these different parameterizations have in common. In other words, we want to focus on the space curve itself rather than how we trace it out, how fast or slow we're going, okay? So if we think about it, we know a little bit about our space curve. So here's our space curve, okay? Now we've learned about the derivative. The derivative of a space curve gives us a vector tangent to the curve at the point. Okay? Now, depending on how we parameterize it, we could, maybe we're parameterizing it so we're going faster. So maybe we're going faster. And if we're going faster, that means our tangent vector is going to be longer, okay? Or maybe we're going slower at this point. And so our tangent vector would be smaller, depending on how we are tracing out that curve, whether we're going nice and slow or whether we're going fast, will determine the length of that tangent vector, okay? Now, as we said, we want to kind of take away those differences. We want to focus on what all what's common to the curve, not how we trace out the curve, okay? So we are going to think about a tangent vector, but not just any tangent vector, the unit tangent vector. So this is going to be the unit tangent vector. It is a tangent vector for any value of t, but it's a unit vector. It's of length 1, okay? And so we calculate it easy enough. We know how to find a unit vector. We take the vector we're interested in, tangent vector we already have, and we normalize it. We divide by the norm. And this allows us to focus on the direction of the tangent vector and not the length. The length of that tangent vector, as I said, it might represent different speeds. We could have two different vectors tangent at that point. The different lengths could represent different speeds of the parameterization, whether we're tracing out that curve fast or slow. All right? What this does is it takes that away. So no matter how we are parameterizing the curve, how fast or slow we're tracing it out, at the point that we reach at time t, we'll always have this unit tangent vector. It will be common to all parameterizations. Okay? Okay, so that's piece 1. That tells us some information. No matter how we're parameterizing the curve, the unit tangent vector is a way to describe the tangent vector to the curve in a way that's independent of the parameterization. Okay? But there's other information to this curve. For example, notice that this curve is kind of bending this way. Okay? It's bending to the left. Down here, it bends to the right, doesn't it? That's going to be true no matter the parameterization, that direction of bend. we want to be able to capture that information too. Okay? So what we want is a unit vector pointing orthogonal to the curve, that points in the direction that the curve bends. We call this the unit normal vector. Okay? And maybe I should put a descriptor here. Unit vector tangent to the curve. And n of t, which I'm not going to give you a formula for yet, the unit normal vector, this is going to be a unit vector normal to the curve or orthogonal to the curve. But not just any vector orthogonal to the curve, unit vector orthogonal to the curve in the direction the curve bends. Okay, we will think about a formula for this in a moment. It is just a little tricky to think about. But before we do that, I want to introduce one additional vector. Okay, in two-dimensional space, this seems to kind of describe everything. But in three-dimensional space, there's one other vector pointing straight out at you, based on how I've drawn this. Okay. So it's pointing straight out at you. Let's see, maybe I'll draw it a little bit. Straight out at you. Okay. And it is orthogonal to both of these vectors. Okay. We call this the unit binormal vector. And notice what's happening in this direction. Absolutely nothing. The binormal vector is a direction where nothing happens. Okay. The tangent vector, that's the direction of motion. The unit tangent vector. Unit normal vector, that's the direction in which you bend. The unit binormal vector, that's the direction in 3 dimensions where the curve isn't doing anything. That's the boring direction. Okay, so unit binormal vector. Okay, and this one actually we can find a formula for, though we'll find a better formula for it in a moment. Because it's orthogonal to both of those other two vectors, we could use the right-hand rule, and it's going to be the unit tangent vector crossed with the unit normal vector. Okay, again, that's a good way to think about the definition. It's a little difficult to actually calculate it with this. Okay, so I'll give you a better formula in a moment. But this is going to be the unit vector. It's also orthogonal to the curve, just like the unit normal vector. But it's in the direction where the curve is doing nothing. It's not bending. It's not, we're not moving in that direction. In the direction the curve is static. Okay, let me give you a better visualization than the one I've drawn here. Maybe I should have used different colors, but you'll get the idea. So I have a 3D calculator here, and I've got a curve set up here. Okay, and notice there are 3 arrows. And they're labeled, if you look carefully, the green arrow right here is labeled T. That's the unit tangent vector. Notice the direction it's pointing in. It is pointing tangent to the curve. Okay? And then we have our orangish vector right here. That's the unit normal vector. Okay? It is pointing in the direction the curve is curving. Okay? Do you see that? The direction the curve is curving. If you look at the curve, that unit normal vector is pointing in the direction where the curve is curving the most. Okay? And then we have this light blue one, that's the unit binormal vector. And it is pointing in the direction where nothing is happening. The curve is not curving in that direction. Okay? There's no motion in that direction. This is the direction where nothing is happening. Okay, so what happens? What happens as we let this move along? Okay, look what's happening. Kind of the unit tangent vector is always tangent. The normal vector is always pointing in the direction where the curve curves. Okay, and the binormal vector always points in the direction where it doesn't. Let me reset it and we'll do it one more time. Okay, let me maybe do a different angle so we can kind of get a different view. Okay, unit tangent vector always tangent to the curve. That orangish one, the unit normal vector, is always pointing in the direction the curve curves, right? Where the curvature of the space curve is. And the binormal vector is pointing in the direction where none of that is happening. Okay, it's not the direction of motion. It's not the direction where we're curving in. The binormal vector is the boring direction. Okay. If you think about it as a roller coaster, the unit tangent vector, that's the direction the roller coaster is moving in. The unit normal vector, that's the direction you're going to feel jostled side to side. If you turn, the unit normal vector is the direction opposite of where you feel like you're being pulled. You feel like you're being pulled one way because the roller coaster on the track is actually curving the other way. It's curving in the direction of the unit normal vector. Okay. And then we have the binormal vector. That's the direction where the roller coaster isn't doing anything. It's not the direction where it's moving. It's not the direction where it's curving. There's nothing happening in that direction. Okay. These three together, the unit normal, the unit tangent, and the unit binormal, they summarize the important directions of motion of a curve in three-dimensional space, regardless of the parameterization. These describing the curve this way, it focuses on the shape of the curve and not how fast we are going along the curve, not how fast we are traversing the curve. Okay, so let's talk about the formulas for these. Now, we already have a formula for the unit tangent vector. That one's easy. We already have a vector pointing in the right direction, right? Given any parameterization, if you take the derivative, it gives us a tangent vector. I just normalize it to get a unit tangent vector, okay? But what about the normal and binormal vectors? So I'm going to use formulas that are a little bit different than the book. The formulas given in the book can be really difficult to work with in practice. These ones will be a little bit easier. It turns out that it's going to be easier to actually calculate the binormal vector first, okay? And let's get some intuition why this works, okay? So let's get some parameterization here of some curve, okay? The unit tangent vector at a point, I'm sorry, not unit tangent vector, a tangent vector at a point is r prime of t. Okay, it's not necessarily a unit vector, but it is tangent to the curve. Okay, now let's think about the second derivative. What's the second derivative tell us? Well, we know this, the derivative is the rate of change, right? It's how fast things are changing. The second derivative tells us the rate of change of the first derivative. It tells us how the first derivative changes. Okay, so this second derivative, okay, maybe we have two things happening. So let me give you an example of what the second derivative might look like. Okay, something like this. And we could break this into two pieces, two components. A component in this direction, in the direction of the unit tangent vector, and a component in this direction. Okay. Now this first component, what that's telling us is how the magnitude of r prime is changing. Okay. In practice, if we're looking at a vector valued function, if we're tracing out the curve, this is telling us how the speed is changing. Okay. So with the way I've drawn r double prime, that means I'm increasing I'm increasing r prime in this direction. I'm increasing its magnitude, which would, in effect, increase the speed of a particle moving in this direction at that moment in time. Okay, the speed would be increasing. Okay, but notice that r prime, there are two ways for it to change. I could change the derivative by changing the length, either speeding it up, making the r prime longer, or slowing things down, making r prime shorter. Okay, or I could change its direction, okay, and leave the speed the same. What looking at these components does is it allows us to look at these two different facets of how r prime can change individually. So the change in the direction of r prime, that changes the speed of a particle moving along this trajectory. Okay? But this one changes the direction r prime is pointing in. This vector here, that vector is pointing in the direction of the unit normal vector. And that's what we want, right? The unit normal vector. Okay? So r prime has these two components hiding inside of it. Now, it's going to be easier, as it turns out, to find the unit binormal vector first. Since, maybe I should color these green, actually. Okay. So unit normal vector points in this direction. It won't necessarily have that magnitude, but it points in that direction. Okay. Notice what that means. That means that the plane containing r prime and r double prime, containing those vectors, is the same plane as the plane containing the tangent vector and the normal vector. Okay. So we could find the binormal vector by taking the unit tangent vector and taking the cross product with the normal vector. But we get the exact same direction if we take the cross product of r prime with r double prime. Okay? So it won't give us the length, but remember, we know the length. We know the length is going to be 1. So our unit binormal vector is going to be the unit vector pointing in the direction of r prime cross R double prime. Okay. Notice I've left off the T here. A lot of time we do that to simplify the notation. I could put the of T, right? There's nothing wrong with that, but it starts to look a little busy, doesn't it? So a lot of times we'll just leave that off and it's understood that these are functions of T. We're just not writing it, okay? So R prime cross R double prime, it doesn't give you the binomial vector, but it points you in the right direction. Once you get the direction, all you have to do is normalize it. Okay, so this will point you in the direction of the binomial vector. In a direction the vector will be orthogonal. I'm trying to figure out a way to draw this so it looks like it actually is. So it'll be pointing straight at you, okay? The vector will be pointing straight at you, and it will be orthogonal to both R prime and R double prime, which means it will also be orthogonal to the unit tangent vector and the unit normal vector. Okay? The unit tangent vector and the unit normal vector help us understand the directions of motion of this space curve. Okay? Okay, so that's the binormal vector. It's pointing directly at us, which means now that we have that one, we can find the unit normal vector pretty easily, because unit normal vector is also orthogonal to both the binormal vector and the unit tangent vector. Okay, so we could, if we know the binormal vector, we could use the cross product of these two to find the unit normal vector. All right, so if I could find two vectors in those directions, I'm good to go. So I'm not going to use the binormal vector or the tangent vector directly. Instead, I'll get a vector pointing in the direction of the unit tangent vector. I'll get a vector pointing in the direction of the binormal vector. Once we normalize things, we end up dividing by square roots. It makes things really messy. So if we could find these vectors with saving that normalizing part till the very, very end, it saves us having to deal with those nasty square roots. Okay? So the unit normal vector will be the unit vector pointing in the direction of, and so I want to take the cross product of a vector pointing in the direction of the binormal vector, so this guy, that's pointing in the right direction, with a vector pointing in the direction of the unit vector. The unit tangent vector. R prime points in the direction of the unit tangent vector. Okay? So this vector is pointing in the right direction. It's pointing in the direction of the unit normal vector. Now, this probably isn't the unit normal vector, but it's pointing in the right direction. And that's the most important part. The length is easy because all we have to do is normalize it. Okay, same thing with the binormal vector. All right, so we can easily find, with some cross products, the directions we need to be in, and then we just normalize the results to get our final answers. Okay, that's true also for the unit tangent vector. Okay, we can easily find a vector pointing in the direction we want, R prime. And then we just normalize it to turn into a unit vector. That way we get a unit tangent vector. All right? All right, let's take a look at a couple of examples. Now, for this first one, we're dealing with a curve, but it's only in 2 dimensions. And so we're only finding the unit tangent vector and the unit normal vector, not the unit binormal vector. Now, that could be a problem. Let me remind you why. Okay, remember the unit tangent vector is the unit vector pointing in the direction of R prime. Okay, The unit normal vector is the unit vector pointing in the direction of r prime cross r double prime cross r prime. Okay? This one's not going to be a problem. I could calculate r prime, no problem. I could normalize it. That'll be relatively simple. This one could be an issue because the easiest formula for describing this unit normal vector involves cross products. There's two of them. But how many dimensions do we need to define the cross product? Normally, the cross product is only defined in 3 dimensions. It only really makes sense in 3 dimensions, right? Because it gives us a vector orthogonal to the first two. If you have 2 vectors in 2 dimensions, and you find a vector orthogonal to both of them, that orthogonal vector will no longer be in those 2 dimensions, right? Well, that's an issue, right? But as we have learned, we can still apply the cross product in 2 dimensions if we embed those 2 dimensions in 3-dimensional space. And sometimes that is useful. This is one of those times. Okay, so rather than thinking about this as a curve in 2D space, we'll think about it as a curve in 3D space, but one that lives only in the XY plane. Okay? Now, we won't deal with that until we get to this part. All right? For now, let's start by finding the unit tangent vector. Notice we don't need to find the general unit tangent and unit normal vectors. We just need to find the unit tangent vector and the unit normal vector when t is 1. And that's going to be useful. Looking at only one value will keep the math a little simpler, as we'll see. Okay, so let's start by finding that unit tangent vector. We first need to get a vector pointing in the right direction. The r prime will give us that vector. So let's take the first derivative of our vector valued function. Okay, and I just take the derivative of each component. So 1/3 t cubed, that's just t squared. 1/2 t squared, that's just t. Okay. So this is pointing in the direction I want my unit tangent vector in. Once I'm in the direction, to make it a unit vector, I just normalize it. Okay, so my unit tangent vector is what I just found, divided by the norm of the vector. All right, now I could do this, and this is fantastic. Okay, but it's actually a little bit easier since I'm done taking derivatives that I need for this if I plug in the 1 first. If I plug in the 1 first, then I don't have to worry about dealing with so many t's. Okay, so if I plug in 1, sorry, not r of t, r1 of r prime of 1, then I get 1 squared I, or just I, plus 1 times j is just j. So it's I plus j, or if you use the angle bracket notation, it would be the vector 1, 1, right? And so all I care about is the unit tangent vector in the when t is equal to 1. So rather than plug all the variables into the formula, this will be a little bit easier to work with. Okay, so in the numerator I just have r prime of 1, and in the denominator I need the norm of r prime of 1. Okay, so in the numerator, vector I plus j. In the denominator, norm will be first component squared plus second component squared. And so I get 1 over root 2i plus 1 over root 2j. That vector will be tangent to the curve at t equals 1. and it's also a unit vector. It has length 1. Okay, so that's the answer to the first part. Okay, now let's get to the second part. Here we're going to need r prime and r double prime. We already have r prime here. Let me copy it down here so we can reference it. R prime of t, it was t squared I plus tj. Right? Yeah. For this formula, I'm going to also need the second derivative. So let's find the second derivative. And this also an easy derivative to find. Okay. And now to find a vector pointing in the direction I want, I'm going to take the cross product of r prime and r double prime. And then when I'm done with that, I'll take the cross product of that result with r prime. Okay? It's important that you get the order right here. You can't just move these around and take the cross product willy-nilly. You got to be real careful how you do this. Okay? Okay. So a few things here first. I don't care about the unit normal vector for every value of t. I just care about it at t equals 1. So before I start taking cross products with variables, which we could do, okay, but it's going to make things a little bit easier if I plug in that 1 first. Okay, so that gives me 1i plus 1j, so I get I plus j. And then for the second derivative, if I plug in that 1, I get 2i plus j. Okay. So I'm going to start with just what's inside the parentheses here, r prime cross r double prime. Okay, so r prime of 1 cross r double prime of 1. And here's where we have to be careful. Because cross products only work in 3 dimensions, we have 2-dimensional vectors, right? I'm going to write it in angle bracket notation. R prime of 1 is 1, 1. And I'm going to take the cross product of that with r double prime of 1, which is 2, 1. How do I take a cross product of two 2 by 2 vectors? Well, the answer is I actually have to embed them in 3 dimensions. So I'm going to embed them in the xy plane. So I'll leave x and y the same, but if it's in the xy plane, that means z is equal to 0. Okay, and I could do that with this one too. Okay, so whenever you take a cross product of 2-dimensional vectors, you need to embed them in 3-dimensional space. All right. So I, j, k, first vector first, 1, 1, 0, second vector second, 2, 1, 0. Take the cross product. For I get 0 minus 0, so no i's. Okay. J, also 0 minus 0, no j's. That shouldn't be surprising if you think about it, right? Both of these vectors are already in the xy plane. So any vector orthogonal to both would be pointing out of the xy plane, just in the k direction. Okay, so k, we have 1 minus 2. So that's negative 1k. Or if, again, if you prefer angle brackets, 0, 0, negative 1. Okay, all right, we're not done yet. All we've done so far is found this bit. Now we're going to take this bit that we've already found and take the cross product of it with r prime again. Okay, so that's r prime of 1 cross r double prime of 1. And then I take the cross product of that with r prime of 1, which was I plus j. And again, I'm going to think about embedding these in 3-dimensional space. So this we've already found, 0, 0, negative 1. And now take the cross product with r prime of 1, which is I plus j. In angle bracket notation, That's 1, 1. And if I embed it in three-dimensional space, the z component is 0. Okay? So let's find the cross product. So I do ijk, first vector first, second vector second. Okay. For I, I'm going to get 0 minus negative 1. So that's 1i. Okay. For j, 0 minus negative 1 again, that's 1j. And then for k, 0 minus 0. So no case. Okay. And then alternate signs, plus, minus, and then plus if I had the k there, which I don't. Which means my vector is 1, negative 1, 0. Okay. This vector is pointing in the direction of the unit normal vector. So it's pointing in the right direction. All I need to do now is turn it into a unit vector. I need to normalize it. Okay. So the unit normal vector is going to be that 1, negative 1, 0. I could just think about it as 1, negative 1. Now, once you're done taking the cross product, you can drop the third dimension. Okay. So I'm back in two-dimensional space here, right? The k component goes away. And then square root of 1 squared plus negative 1 squared. I'm taking the norm of it to turn it into a unit vector. Okay, and so I get 1 over root 2, negative 1 over root 2. Or if you prefer ij notation, which we probably should since that's what we started with, let's stick with the notation. That'd be 1 over root 2i minus 1 over root 2j. And so we found the unit tangent vector and the unit normal vector. Okay. Now what I'd like to do is I'd like to graph these for you so you can see that they really are tangent to the curve. This one will be tangent to the curve when t is 1. And this one will be pointing in the direction that the curve curves, okay, at t equals 1. Okay, so let me pull it over. All right, so let's start by plotting the curve itself. The curve was 1/3 t cubed I plus 1/2 t squared j. One third t squared was the first component. Sorry, no, wait, which one was it? 1/3 t cubed, comma, and then the j component was 1/2 t squared. And to just make sure we get a full picture, let me go from negative 10 to 10. Okay, so we have this very interesting curve. Okay, now let's plot the unit tangent vector. So this is going to be when t is 1. So I'm going to start off by plotting the point. The point itself would be 1/3, 1/2. Right? When t is 1, I get 1/3, 1/2 right there. Okay, leave that blue. So unit tangent vector starts at this point. I want to draw the unit tangent vector starting from that point, and then I want to go in the direction of the unit tangent vector, which is 1 over root 2, 1 over root 2. Okay. Pick a color that contrasts a little bit better. Do you see how it is actually tangent to the curve there? Okay. It doesn't have an arrowhead that you can see that it is tangent to the curve. Okay. I want to do the same thing with my unit normal vector, which is almost the same, just the j component is negative. I'll just copy this. and make the second component negative. Pick, it's actually a pretty good color. Okay. So this vector here, it's missing the arrowhead, but otherwise this is the correct vector. And notice it is at a right angle to the curve, but also it is in the direction where the curve curves inward, right? It's pointing out from where the curve is concave. Okay. And so independent of the parameterization, these two vectors tell us the direction that's tangent to the curve at that point and the direction which is orthogonal to the curve in the direction where the curve is concave. Okay? Let's do another example. This one's a little more difficult. The space curve actually is in 3 dimensions. And here we want to find the unit tangent, the unit normal, and the unit binormal vectors. Okay? So remember unit tangent, unit vector in direction of r prime, unit normal is the unit vector in the direction of r prime cross r double prime cross r prime. And the unit binormal vector is the unit vector in the direction of r prime cross r double prime. Okay? Now again, we only care about the values of the unit tangent, unit normal, and unit binormal vectors at a particular value. And so we can use that to make the calculations a little bit easier if we plug in at the right point. Make sure you plug in after you take the derivative. We need the variables there so we know the derivative. But as soon as you take the derivative, you could plug in. Okay? So looking at what we need here, we're going to need the first derivative. Okay? And we're going to need the second derivative. So let's take the derivatives of our parameterized curve. And then we can plug in t equals 0 after we take the derivative. Okay? So r prime, well, let me rewrite r of t first, a little bigger so it's a little easier to see. And I think I'll write it in angle bracket notation. I like angle bracket notation better. And I think it is a little easier to mentally separate the different components. Okay? So first derivative of t is 1. Derivative of e to the t sine t and e to the t cosine t. We're going to need a product rule for both of those, right? So derivative of e to the t sine t, derivative of e to the t is e to the t. Leave sine t unchanged, and then swap. Now I'm leaving e to the t is unchanged and taking the derivative of sine of t, which is cosine of t. Okay? And we want to do the same thing here. Another product rule. Derivative of the first guy, derivative of e to the t, is e to the t. And then leave cosine of t unchanged. Plus, now you swap. Now you leave e to the t unchanged, and you multiply by the derivative of cosine of t, which is negative sine of t. Okay? All right. And if you thought that was fun, we've got one more to go. Second derivative. Okay? Derivative of 1 is 0. That one's easy. Derivative of e to the t sine t plus e to the t cosine t. Well, we just found the derivative of e to the t sine t. and we found the derivative of e to the t cosine t. So rather than thinking super carefully, I can use those derivatives I've already found and plug in. All right? So e to the t sine t plus e to the t cosine t, when I take the derivative, this is the derivative of e to the t sine t. This is the derivative of e to the t cosine t. Let's combine them. What's going to happen if I add them together? I get e to the t sine t, and negative e to the t sine t will cancel. And so, you know what? Let me write it all out, because I'm canceling things that aren't really canceling. Let me write it down here. Okay. That's the derivative of e to the t sine t, because I already found it. Okay, so I'm taking the derivative of this guy. Right? And now for e to the t cosine t, I already did a derivative of e to the t cosine t, so let's just plug that in. Don't have to do a whole lot of thought here. I get e to the t cosine t minus e to the t sine t. Okay, now that's just my second component. Okay, let's do our third component now. Give myself some space. Maximize our viewing area. There we go. There we go. And we could do the same thing. This is just the derivative of e to the t cosine t, e to the t sine t. I already found those when I found r prime. So let's do e to the t cosine t first. Derivative of e to the t cosine t is just this. Okay? So derivative of e to the t cosine t is e to the t cosine t minus e to the t sine t. Okay? And then minus, and now the derivative of e to the t sine t, which I did when I found r prime. This is the derivative of e to the t sine t. So I'll just plug that in. Derivative of e to the t sine t is e to the t sine t plus e to the t cosine t. Okay. That's a long vector. Let's see if we could tidy things up before we move on. Okay, first component's still 0. If we look here, though, I have e to the t sine t plus negative e to the t sine t. Those will cancel. Okay, leaving me e to the t cosine t plus e to the t cosine t. That's 2 e to the t cosine t. Okay, and that's all that second component is. All of this just simplifies to that. Okay, and let's do the third component. We get something similar going on here. I get e to the t cosine t minus e to the t cosine t. Those cancel. Okay, and then I have negative e to the t sine t minus e to the t sine t. So I'm going to get minus 2 e to the t sine t. Okay. Whew. Fair bit of work taking those derivatives. But the rest is pretty straightforward. Now that I've taken the derivatives, I don't really need the variables anymore. I could just plug the t equals 0 in. For everywhere else I'm going to be using them, I just want r prime and r double prime at t equals 0. So let's plug in t equals 0 for r prime right here. So if I plug in 0, this is a 1. That just stays a 1. E to the 0 is just 1, so I don't really have to worry about those. Sine of 0 goes away. Sine of 0 is just 0. So I just get cosine of 0. That's a 1. Okay? And something similar happens here. E to the 0 and e to the 0 are 1. Sine of 0 is 0. Cosine of 0 is 1. I just get 1 again. So r prime is 0. All this, once I plugged in the 0, it's just 1, 1, 1. Okay? Same thing for r double prime. First component of r double prime is a 0. Second component, if I plug in 0 for t, e to the 0 is 1. Cosine of 0 is 1. Times the 2, I get 2. Okay? And last component, e to the 0 is 1. Sine of 0 is 0. Times the negative 2, that's just 0 because sine of 0 is 0. So I get 0, 2, 0. Okay? So these are the vectors I'm going to use when calculating my unit tangent, unit normal, and unit binormal vectors. Okay? All right. First things first. Let's do unit tangent first. So unit tangent at t equals 0. It's pointing in the same direction as the first derivative, but I need to normalize it since I want it to be a unit tangent vector. Okay? So I just get 1, 1, 1 divided by the norm of that vector. So norm of 1 squared plus 1 plus 1 squared, that's going to be 3. So square root of 3, I get 1 over root 3, 1 over root 3, 1 over root 3. Okay? First one's done. That's the unit tangent vector. Okay? Now next, I could do the unit normal vector, but I notice that this bit of the unit normal vector, it's just this, right? The calculation I would need to find my binormal vector. So rather than doing the unit normal vector first and then having to redo this, let's find the unit binormal vector first. And then once I do that, I'll have that first bit of the calculation for my unit normal vector. And I'll only need to do one more cross product. Okay? So unit binormal vector next. We'll do r prime cross r double prime. Let me box this one so we remember that's one of our solutions. So unit binormal vector, actually, I won't calculate it directly yet. We want r prime of 0 cross r double prime of 0. Now remember, this isn't going to give us our unit binormal vector. This gives us a vector pointing in the right direction. Once we get it, we have to normalize it to get our unit binormal vector because our unit binormal vector has to be a unit vector. Okay? So r prime of 0, that's 1, 1, 1. R double prime of 0 is 0, 2, 0. So I want 1, 1, 1 cross 0, 2, 0. And I'll do this cross product pretty fast. Okay, first vector first, 1, 1, 1, second vector second. Okay, I component, I get -2. J component is 0. K component is 2. Right? That's pointing in the direction I want it to be for my unit binormal vector. To finish it off, I just need to normalize it. Change it into a unit vector. So -2, 0, 2. Divide by, now I want to divide by the norm. The square root of -2 squared is 4, plus 0 squared is 0, plus 2 squared is 4. So I end up with a denominator of the square root of 8. Okay? And so if I do the division, I get -2 over root 8, 0, 2 over root 8. And if you remember your roots, it's pretty easy to see root 8 is just 2 root 2, right? Because 8 is 2 times 4, and the square root of 4 is 2. So we could pull a 2 out of the root, and so I get 2 square roots of 2. If I were to make both these 2 square roots of 2, the 2 in front would cancel with the 2 on top. And so this simplifies to -1 over root 2, 0, 1 over root 2. Okay? Part 2 done. Right? We got our unit binormal vector. Final step, we need our unit normal vector. R prime cross R double prime cross R prime. So unit normal vector at 0, R prime cross R double prime cross R prime. Okay. Now again, this isn't going to be the unit normal vector, but it's going to be pointing the right direction. We need to normalize it when we're done to find the unit normal vector. Okay. We've already found this. It's this right here, right? -2, 0, 2. So let's plug that in. We already found this. -2, 0, 2. That's what that is. And then we just need to take the cross product of that with r prime. If we go back, r prime at t equals 0 is the vector 1, 1, 1. So cross with 1, 1, 1. First row ijk, second row -2, 0, 2, third row 1, 1, 1. And again, I'm going to move pretty fast here. I get -2. J is -2 minus 2, so that's -4, but because it's J, the sign switches, so that's +4. And K, I get -2 again. Okay? Now all we need to do, so this is the vector pointing in the direction of the unit normal vector. Now all we need to do is normalize it to get a unit normal vector. Okay? So that's -2, 4, -2. I'm going to normalize it. So I'm going to take the square root of the sum of the squares. -2 squared is 4. 4 squared is 16. -2 squared is 4, so that's 4 plus 16 is 20 plus 4 is 24. Okay, root 24. Root 24, we can simplify that a little bit. Root 24 is 4 times 6. And since the square root of 4 is 2, I get 2 square roots of 6. So divide each component by 2 root 6. The 2 will cancel in each case. So -2 over 2 root 6 simplifies to -1 over root 6. 4 divided by 2 root 6 simplifies to 2 over square root of 6. And -2 over 2 root 6 is, again, -1 over root 6. And that gives me my unit normal vector. Okay? So the unit tangent vector, remember, that is a unit vector pointing tangent to the curve. Unit normal vector is a unit vector pointing in the direction where the curve is curving into. Okay, the pointing out of the part of the curve where it's concave. And the unit binormal vector is the direction where there's nothing happening at all. All right, let's plot it so we get an idea of what's going on. Let me do that. So let's start by plotting the curve. The curve was t e to the t sine t, e to the t cosine t. T e to the t sine t, e to the t cosine of t. Okay, and let's go -10 to 10. Get a good range going here. Let's leave it blue, I think. Okay, so there's our curve there. Let me lose the xy plane. I think it makes it a little harder to see. Okay, all right, the point that we're interested in is the point when t equals 0. So if I plug in 0 into this vector valued function, I get 0, 0, 1. Okay, so it's that point that happens to be right on the z-axis. Okay, make it just a little bigger so it's a little easier to see. It's a little too big. That'll do. Okay, now that's the point we're interested in. So let's start by plotting the unit tangent vector. The unit tangent vector at that point was 1 over root 3, 1 over root 3, 1 over root 3. Okay, so I'm going to start the vector at the point, and then I'm going to add 1 over square root of 3, 1 over square root of 3, 1 over square root of 3, t. Okay, and you can see that that vector, it really is tangent to the curve. Zoom in a little bit. Let's focus in on it. Okay, you could see that it's tangent to the curve right there. So we're telling the truth. We're getting the unit tangent vector. Okay, just missing the arrowhead again, but otherwise this is the unit tangent vector. Okay, let's plot the unit normal vector. So it's negative 1 over root 6, 2 over root 6, negative 1 over root 6. So I'm going to make sure I start at the same point. Plus negative 1 over square root of 6, 2 over square root of 6, 1 over square root of 6 t. Okay? Maybe I'll make this one green. Okay? It is orthogonal to the curve, and it's pointing in the direction the curve is curving. Right? That's the concave side. Okay, one more. Let's do the unit binormal. There should be nothing happening in that direction. So that's negative 1 over root 2, 0, 1 over root 2. So make sure I start at the point. Negative 1 over root 2, 0, 1 over root 2, t. Okay, and you could see that direction. It's also orthogonal to the curve. And it's pointing in the direction where nothing is happening. And actually, there's something wrong here, isn't there? If we look carefully, these three vectors, they should all be orthogonal to each other. And the green vector, it's not doing what it should. Let's check our work there. So I got 0, 0, 1 plus negative 1 over root 6, 2 over root 6, 1 over root 6t. See, it should be a negative there. I dropped the negative. So let's add a negative in there. Okay, that looks a little more convincing, right? It is, okay, yeah, that's definitely orthogonal to the curve. I was trying to convince myself of it before. Definitely orthogonal to the curve, but it definitely also is in the direction where the concavity is, right? So we got our three vectors as expected, and it's independent of the particular parameterization. At that point, no matter what the parameterization is, if you're going in this direction, you'll always get that unit tangent vector, that unit normal vector, that unit binormal vector. So next we're going to talk about arc length. And this feels pretty different than what we've just been doing, but it's going to help us with the same goal eventually, which is to help us describe the geometry of a parameterized curve independent of how we parameterize it, independent of how fast or slow we traverse that curve, okay? So the derivation of a formula for arc length is pretty straightforward if you're comfortable with integration, okay? So the idea here is we use a trick that we often use when we want to use integration with something. Rather than look at all of this at once, we're going to approximate it by a lot of little pieces here. Okay, so if I could find the length of all these vectors, then it'd be a pretty good approximation, wouldn't it? Okay, and I could improve the approximation as I increase the number of vectors. And if instead of doing this, if instead I have lots of little smaller vectors, then my approximation would improve, wouldn't it? Okay, I'm not going to draw them all, but you get the idea. Okay, eventually we want to look at the limit as the number of vectors goes to infinity and the size of the vectors go to 0. All right, and that's what we do when we want to do integration. We add up a bunch of pieces that grow infinitely many, but infinitely small. Okay, so I'm going to let S represent arc length. Okay, and what I want to do is I want to add up all these little curves, all these little vectors, and I want the length of the vectors. Okay, now I'm going to approximate these vectors rather than calculate these vectors directly. You know what? Let's calculate them directly. Let's calculate them directly. Okay. What I want to do is I'm going to, for each t, I'll go from my starting point to my ending point. Okay. And if I look at the points connecting them, then I can calculate the vector here, each vector by vector subtraction, right? End minus start. So I want to end at this point and start at this point, okay? So I want to start here at ti, okay? So maybe this is t0, this is t1, this is t2, and so on, okay? And then my next point would be ti plus 1. But a better way to do this, if I have, if I'm spacing out the t's evenly, I could just say how much I'm spacing out the t's by. Okay, and then I want the norm of this because I want the lengths of these vectors, right? And I should say this isn't equal to s. This is an approximation. Now, if you've done a lot of calculus, this looks awfully familiar, right? This is the numerator of our derivative function, isn't it? So what if we kind of complete it? R of ti plus delta t minus r of ti, and then I just divide by delta t. And I can do that as long as I also multiply by delta t. Okay, and because delta t is a positive, it's just how far the t's are from each other. I can move it in and out of the norm as I wish. Okay. Okay, so now, hey, this is looking like a derivative, doesn't it? So now let's just make the approximation exactly equal. We can do that by either letting the number of pieces go to infinity or the size of each piece go to 0. Effectively means the same thing. So let's let the size of each piece go to 0. That means n would get bigger because I'd have more pieces that I would have to use to span the entire curve, right? And this is something that we should recognize. If there is, you from calculus 1, you learned about Riemann sums, okay? You may have learned formulas for dealing with summation formulas. Here's what I really want you to remember. When we have a summation like this, where we're taking something and then we multiply it by something else, and that something else is getting smaller. Okay, we have an infinite number of pieces. The number of pieces goes to infinity as the size of each piece goes to 0. We are dealing with integration. Okay, the limit of this ends up being the integral from wherever we start to wherever we end. Okay, so t naught to tn of this, but because we're letting delta t go to 0, what does this become as delta t goes to 0? Well, by definition, we get the derivative, don't we? So we get the norm of the derivative of r and then the delta t becomes dt. Okay? If there's something you need to remember about integration, remember this. These are the same. Okay? With the exception of this. That's a little extra step that we don't always use when we do integration, but it's part of the same limit. Okay? As these get 0, that just as this gets smaller to 0, as delta t gets closer to 0, this gets closer and closer to the derivative r prime. Okay? But more importantly, when we have a summation, the number of items goes to infinity, and then we have something multiplied by delta t, and the delta t is going to 0, and that means integration. The delta t becomes dt, the summation becomes an integral, and what's ever inside here, that's the integrand. Okay? And so we've derived a formula for finding the arc length. Given a smooth parameterization R of t, and by the way, smooth parameterization, that means the normal stuff. We means we can take the derivative. It also means that the function doesn't double back on itself. Okay, so if we want to map this this curve, we don't want a parameterization that goes this way and then doubles back and then comes back this way, right? Because then we'd be double counting portions of the curve. So if we want an accurate measurement of the length of the curve, not the distance of how far we've traveled, but the length of the curve, we need to not be able to double back on ourselves. Okay? So given a smooth parameterization R of t, the arc length of the curve traced out by R of t from t equals a to t equals b is s equals the integral from a to b of the norm of the derivative of the parameterization integrated with respect to t. Let's do a quick example. We have a vector function. Let me give this angle brackets. There we go. We have a vector function r of t, and we just want to find the length of this this curve, starting at t equals 1 and ending at t equals 4. Okay, so all we do is plug into the formula. Okay, the arc length is the integral from t equals 1 to t equals 4, so those are our limits of integration. And then we're going to take the norm of the derivative. So we're going to have to find the derivative. Okay, so looking at our function here, derivative is pretty straightforward. Just take the derivative of each component. 2t squared plus 3, just a couple power rules. Derivative 2t squared is 4t, and derivative 3 is 0 since it's a constant. Similarly, derivative t squared plus 1 is just 2t. And then the derivative of 1, of course, is a constant. So there's our r prime. We need the norm of r prime. So let's go ahead and plug that in. And we want this with the t so we can integrate it. Right? We need to capture the changes that the variables bring in order to integrate. So we don't want to plug anything in until after we integrate. So norm of r prime, that's the square root of the first component squared, so that'd be the 4t squared, plus the second component squared, that's the 2t squared, dt. Okay, 4t squared is Square both of them, that's 16t squared, and then 2t all squared, I get 4t squared. I can add them together. 16 plus 4 is 20, so I get root 20 t squared. Okay. Now this actually simplifies pretty nicely. Root 20, that's a constant, and I could pull it out of the integral, right? When I'm multiplying by a constant, I could pull the constant multiple out of the integral. So I'm going to get root 20 out here. But while I'm pulling it out, let me go ahead and simplify it. 20 is 4 times 5. So I could take the square root of the 4, that's 2, leaves me with a 5 under the root. Okay, so square root of 20 is just 2 times 5, and I left that outside the integral. Right? Now what about the square root of t squared? Now normally we have to be very careful with this. Generally, the square root of something squared is the absolute value of that something. Okay, so this would be the absolute value of t. And integrating the absolute value of t, how do you deal with the absolute value? Well, it's pretty gnarly. Okay, fortunately, we don't have to because we're not looking at every possible t. Our t's are only ranging from 1 to 4. Within that range, the t is always positive, which means I can drop the absolute value. So 2 root 5, and I'm going to integrate just t from 1 to 4. Okay, now that I've done all the simplification, this is pretty easy, right? Just the power rule. So 2 root 5 out here, and then the antiderivative of t is t squared over 2, and I'm going to evaluate that from t equals 1 to t equals 4. Okay, before I plug in, I'm just going to go ahead and cancel this 2 with that 2. And so I get root 5 on the outside, and on the inside I get 4 squared minus 1 squared. Just plugging in 4 and 1 into the t squared and subtracting. 4 squared is 16, 1 squared is 1. 16 minus 1 is 15. My final answer is 15 root 5. That is the length of this curve from t equals 1 to t equals 4. So now we know how to find the arc length of a curve, right? The formula is S equals the integral from a to b of the norm of the derivative of a smooth parameterization of the curve integrated with respect to t, right? The idea here is that it will give me the total distance from a starting point at t equals a, okay, to an ending point at t equals b. And it'll tell me the length of the curve, the total distance traveled to traverse this curve. All right? But we can actually generalize this a little bit. Instead of looking at just the arc length from a to b, we could actually turn this into an arc length function that will tell us the arc length from a starting point to any value that we choose along the curve, any t along the curve, rather than having to go all the way to the end. Okay? So to do that, we want to change b to t. That way we're going from our starting point t equals a to some other variable point t that we can choose. Okay, now because we are using variable t here, we don't want to use variable t here. We need some other dummy variable. You don't usually have the same variable in your limits of integration as you have inside the integral. So I'm going to just use a dummy variable here. So I'll just swap out t for something else, some other letter. Say u. Okay. Now, for different values of t's, this is going to give me a different arc length, right? Starting from t equals a and then going to whatever t that I choose. So maybe I choose the t that gets me that far, and it'll give me the arc length of that portion of the curve. This is now a function of t. It's not just a single arc length, but it's an arc length function. For different values of t, it will tell me the arc length from a to t. Arc length function. Okay? And one useful observation here, we can use the fundamental theorem of calculus to find the derivative of this arc length function. Okay, if I want the derivative of the arc length function with respect to the variable t, then that means I want the derivative with respect to t of this integral, right? But what happens when you take the derivative of an integral? They're opposite operations, aren't they? And so they'll undo each other. Okay, so by the fundamental theorem of calculus, the derivative and the integral undo each other, and all I'm left with is the inside, and just using the actual variable though instead of the dummy variable. So I end up with r prime of t in a norm. Okay. So for future reference, that is the derivative of the arc length function. It will come in handy later. Okay. Now, we can actually do something pretty cool with this arc length function. One of the things that we're looking at in this section, and I've mentioned it before, we want a way to describe the curve without worrying about the parameterization, how fast or slow we're going, right? This arc length value, this arc length function, it gives us a way to standardize the parameterization for a curve. It gives a kind of a clear way to describe any curve without having to worry about the parameter, because we're going to standardize which parameter we use. If we use the arc length itself as a parameter, okay? If we use the arc length itself as a parameter, then we start at 0, because at the starting point we've gone 0 units. If I go to s equals 1, okay, then I have traveled 1 unit along the curve. Okay, if I travel 2 units along the curve over here, now I'm at s equals 2, and so on. So I want to find a parameterization for the curve that uses the arc length as the parameter. If I'm plugging in s equals 3, then the point this parameterization gives means that I've traveled 3 units from the starting point. Okay? So how do I do that? Well, I already have the arc length function. Okay? So this will be different. This is calculated different for every problem, but this is the first step, perhaps the most important step. Okay, this is the arc length function. It will give you a relationship between the arc length s and our original parameter t. So it gives the relationship between the arc length and the original parameter t. Okay, and then what you do is you go back to your original parameterization for the curve. Original parameterization from the curve of the curve. Okay, and because you have a relationship between s and t, you could solve for t in terms of s and swap out the t in the equation, in the function, for s. Okay. Now for each problem, it's going to be a little different because your norm of the derivative will be different, so your integral will be different, so the exact relationship between s and t will vary. But this is always the the procedure we use. We evaluate the arc length function by taking the integral. That gives us a relationship between our arc length parameter s and our original parameter t. With that relationship, we can go to our parameterization, our original parameterization of the curve in terms of t, and swap it out with the arc length parameter s, because we have that relationship. That will give us a way to traverse the curve using that arc length parameter, and it will make the curve a little bit simpler to work with. It'll allow us to focus on the shape of the curve rather than how fast or slow we're going along the curve. Okay? Let's take a look at an example. Here we want to find the arc length parameterization starting from t equals 0 for this curve. Okay? And we want to have the same orientation as the original curve. That means if we're looking at a curve and we're starting from here, we want to measure our arc length from here also. So we're going to measure our arc length from this side, not from this side. Okay? Generally, unless you really try, an arc length parameterization will have the same orientation as your original curve. So you don't really have to worry about that. It kind of pops out automatically. Okay? So the very first thing we need to do is we need to find a relationship between the new parameter we want, an arc length parameter, with our original parameter t. So we need to calculate the arc length function. So s of t equals the integral from our starting point. We want to start at t equals 0. And we're going to integrate to a variable t. That allows us to find a relationship between s and t. Okay? And the integrand, what goes inside the integral, is the norm of the derivative. And then I want to use a dummy variable since I've already used variable t here. Okay? All right, let's work on taking that derivative. Okay, so this should be r prime, and the only thing I'm doing differently that's a little strange is I'm swapping out all the t's for u's because I want to reserve t for the limits of integration. Okay, so let's take a look at our function here. So here's our function. First component is cosine t. The derivative of cosine t is negative sine t. So that's what I write here. And just swapping out that t for a u. The derivative of t is 1. And the derivative of sine t is cosine t. And again, swap out t for u using that dummy variable. And we want to integrate with respect to u. Okay? All right, next, let's actually take the norm. So square root of the first component squared plus the second component squared plus the third component squared. Integrated with respect to u. Now in this particular case, the integrand is really nice because all the variables drop out. Generally, that doesn't have to happen. Okay, but in this case, because sine squared plus cosine squared is 1, all I get is square root of 2. Okay, square root of 2 is just a constant, and it's really easy to take the antiderivative of a constant. The antiderivative of a constant is just a constant times your variable. And I want to evaluate that variable from 0 to t. So plug in the top limit minus what you get when you plug in the bottom limit, and I just get root 2t. Okay, that is our arc length function. What this does is it gives me an easy way to find the arc length for any value of t. What's the arc length after I go 5 units? Well, just plug 5 in. Okay, it's going to be root 2 times 5. That's the total distance you have traveled when your parameter is 5. After you've traveled this using this parameterization for 5 seconds, okay? Or 5 units of time. Okay, so we have our arc length function. What we want to do is we want to take our same parameterization, but instead of t's, we want our arc length parameter s, okay? Because we have a relationship between s and t, and let me drop the of t because it's going to make things too busy. We kind of want to think of these separately, okay? With this relationship between s and t, I can solve for the t. So s over root 2 equals t. And then I could plug this in to my vector valued function. Okay, so my original vector valued function, in terms of the original parameter t, was cosine t, t sine t. Cosine t, t sine t. But now I have this relationship between s and t, and because I've isolated the t, I could just substitute in what this is to get an arc length parameterization for the same curve. So r of s is going to be, so instead of cosine of t, I swap out the t for s over root 2, so I get cosine of s over root 2. Second component, instead of t, I swap it out for what t is in terms of s. T is s over root 2. And instead of sine of t, I'm going to have sine of s over root 2. Okay, and that's my answer. That's the arc length parameterization. It is a standardized way to describe the trajectory of, to describe this curve, okay? To describe the trajectory of this parameterized function without having to worry about speed or direction, anything like that, okay? Notice what it tells us. It makes it real easy. If I plug in a value of s, it tells us the point that I would be at on the curve after traveling that distance. So if you plug in 2, then cosine of 2 over root 2, 2 over root 2, sine of 2 over root 2, that is the point you would be at on the curve after traveling 2 units. Okay, so this would be s equals 0. This point at s equals 2 is the point you would be at after traveling 2 units, an arc length of 2 units. Okay? So if ever we want to focus on just the shape of the curve without having to worry about how fast or slow we're traversing it, we use an arc length parameterization. Okay? Just a word of caution. We're learning about how to find these things, this arc length parameterization in this section. You'll notice, which one would you rather work with? Which one do the numbers look better in? Well, definitely in the first one, right? The second one, and this was a pretty easy arc length parameterization problem. But in this one, we have these root 2's all over the place. That makes things a lot nastier to work with, right? A lot of times in practice, we use this arc length parameterization to develop the theory initially, and then extend that theory to work with any kind of parameterization. So we rarely calculate arc length parameterizations in practice. It's more of a theoretical concept to standardize the description of these curves. Next, let's take this new tool we have, arc length parameterization, and let's use it to help us to better describe some of the behavior of these curves. Okay, so say I have some curve, something like this. Okay, some curve in space somewhere. Now, what would we like to describe about this curve? With parameterization, we could already describe the position. But one of the things that we notice right away about a curve is that it tends to be curvy, right? A curve has curves. And in some places, we kind of have this intuitive feeling that it is curvier than at other places. Like up here, it's got a curve to it, but it's kind of a gentle curve. Whereas right here, it's a sharper curve, isn't it? It's curvier. It's got more curvature. What we want to do is we want to get a way to define curvature for a vector valued function like this, for a curve like this. All right. So how are we going to do that? Well, our intuition is that kind of the sharper the turn is, the curvier it is at a point, right? So right here, the turn's pretty sharp. So quite a bit of curvature. Whereas down here, this point, there's a turn, but it's a much gentler turn, so less curvature, right? So what we could do is we could look at how, let me draw it a little bigger, how the tangent vector is changing at the point, right? How the tangent vector is changing at the point. Here, it's a gradual change, whereas over here, the change is much more dramatic, isn't it? Okay, so we could look at the tangent vector, but we need to make sure that we're measuring the right thing. We don't just want to take the derivative of an arbitrary parameterization for the curve, because the derivative of an arbitrary parameterization, it's telling us two things. It's telling us how second derivative. The second derivative tells us how the tangent vectors change in two ways. It tells us how they curve, right? Because you could change direction. So it does tell us that. The second derivative tells us how the first derivative changes. So it's telling us how these vectors are curving, how they're changing direction, but also if they're changing their magnitude, it would encapsulate that. That is, if we're start going slow on this curve and then we start going faster. As we go faster, the magnitude of those tangent vectors increases. And the second derivative would capture that information. Okay? So we don't want to, the curvature shouldn't depend on how fast we're going around the curve, right? Curvature should be independent of the parameterization. It should just depend on the direction. So rather than looking at how r prime changes, which would be the second derivative, right, r double prime, since we don't want to focus on the magnitude, we want to only focus on vectors of a set length, tangent vectors of a set length, unit tangent vectors, okay? So the curvature of a smooth curve is given by and we use this here, this symbol here, that's the Greek letter kappa. It looks like an uppercase K, but it's sized like a lowercase letter. Okay, is going to be the rate of change of our unit tangent vector. So we don't have to worry about how the tangent vector is changing length. We only want to know how the tangent vector is changing direction. and we want to know the magnitude of that change. Okay, we really don't care about which direction it's changing. We just want to know how curvy it is. How much is it changing? Okay. Now, even still, even here, this still isn't quite right. If I had this the unit tangent vector at some arbitrary parameter t, then for different parameters t, we're going to get a different curvature, right? Because how quick you change depends on how fastly you're traversing the curve. If I'm traversing the curve slowly, then I'm turning slowly, aren't I? Okay, but if I traverse the curve quickly, then I'm turning much more quickly. With an arbitrary parameter t, it captures those differences. And we want a way to define the curvature so that it's consistent for any parameterization. All we care about is the shape of the curve, not how we traverse it. Okay, so rather than dealing with an arbitrary parameter t, let's have a standardized parameter. And this is where what we just talked about before comes into play. We're going to define the curvature as the magnitude of the rate of change of the unit tangent vector using the parameter, the arc length parameter s, with respect to the arc length parameter s. Okay, that makes sure that the curvature is not dependent on the parameterization. For a curve, it will be consistent always. Okay, the curvature is consistent always. It is measuring how curvy something is. And so now, the way this is defined, it's just how much the direction is changing as we move along the curve. Okay, so here, the direction is changing a little bit. Okay, so it's a little curvy. And then down here, the direction is comparatively changing a lot more, so it's a lot curvier. Has a lot more curvature over here than it does over here. Okay? So that is the definition of curvature. Now, if you've had any practice with calculating an arc length parameterization and dealing with arc length parameters, you'll know that this is a great definition in theory, but in practice, it's going to be hard to compute. Arc length parameterizations can be tricky to work with, tricky to compute and tricky to work with. A lot of times you get square roots in nasty expressions, and it's just not pleasant. So what we would like to do is we would like to find another way to express curvature so it's equivalent to this, but that we can express it in terms of any arbitrary parameter t. Okay? All right, so how do we do that? Well, there's a key observation here, and it's that if you take the derivative of the unit tangent vector with respect to t, you can break that into two derivatives using the chain rule. And actually, let me write this a little differently. So the derivative of a unit tangent vector with respect to whatever kind of parameter you want t is going to be the derivative of the unit tangent vector with respect to the arc length parameter s, that's the one we want to use, okay, times the derivative of the arc length parameter s with respect to the original parameter t. Okay, this is just the chain rule, right? If I want to take the derivative of this with respect to that, I could first take the derivative with respect to a different variable, then multiply by the derivative of that different variable with respect to the original variable t. Right? Classic chain rule. But what I know is that, hey, this has the derivative of the arc length of the unit tangent vector with respect to the arc length parameter s. That's exactly what I want here. T prime of s, that's the same thing as dt ds, right? So let's isolate this in the expression by dividing both sides by ds dt. Okay, so dt dt divided by ds dt. That is dt ds. Okay, Now this is looking a little nicer because now up here, I just have to find the derivative of the unit tangent vector with respect to some arbitrary parameter t. I don't have to go to the arc length parameter, but I still have this down here. Okay. Recall though that when we were dealing with our arc length function, okay, that the derivative of that arc length function will always be the norm with respect to the parameter t, will always be the norm of the derivative of the parameterization in terms of t. So I could plug that in here and then notice, look at this. Is there any s in there? There is not. So I can get rid of that arc length parameter entirely. So I have the derivative of the unit tangent vector with respect to our arbitrary parameter t divided by, and then instead of ds dt, I could write in the norm of r prime. Okay, and now we're basically done. Our curvature is just the norm of the derivative of our unit tangent vector with respect to the arc length parameter s. We have just the derivative of the unit tangent vector with respect to the arc length parameter s. To get the curvature, we need the norm. Okay, so the curvature then would be the norm of this guy, and I'm going to go back to using the prime notation, t prime of s, which would be equal to the norm of this, since these two are equal, right? And dt dt would be the derivative of the unit tangent vector with respect to t. Again, just going back to the prime notation. Divided by the norm of r prime of t. Okay, I literally just plug this in here in between the two norms. Okay, since that's what we need. And then one last thing just to tidy things up. Remember, if you have a scalar inside a norm, you could always take the absolute value of that scalar outside the norm. And since this is already positive, I can write this as the norm of the derivative of the unit tangent vector with respect to some arbitrary parameter t divided by the derivative of r prime of t. Okay, this is a much more workable formula for the curvature than this one over here. Okay, because we don't have to deal with the arc length parameter at all, which is very nice. Even though this definition over here is the one that makes more intuitive sense. This one's going to be the easier formula to calculate. So let me summarize an alternative formula for the curvature. For the curvature of a curve parameterized by r of t. That curvature just the norm of the derivative of the unit tangent vector using t as the parameter divided by the norm of r prime of t. Okay. We have a formula for the curvature, and it doesn't involve the arc length parameter, and that's great. Okay. But if you actually try to use this formula, it's hard to work with. Okay. By no means impossible. But finding the unit vector, the unit tangent vector involves normalizing. And that means we're going to get a square root. And then we need to take the derivative of that expression involving a square root. And it can get really messy really quickly. Okay. So I'd like to derive one more formula for the curvature that's a little bit difficult to derive, but it'll make our calculation for the curvature much easier. Okay? Now, our focus is going to be up here on the norm of t prime of t. Okay? Norm of r prime, that's not an issue. That one's easy to work with. But we would like a nicer, easier expression for the norm of t prime. Okay? To do this, we're going to need two properties. One is called the triple cross product. It turns out that if you take three vectors and take their cross product, notice I'm being very careful with the order here. Notice the parentheses. So u cross v cross w, that is the same as u dot w times v minus u dot v times w. Beautiful. Okay. I'm not going to derive this. It's not an especially interesting proof. You literally just, you do the cross product on this side, you do the dot product and the scalar multiplication on this side, and you realize it's the same thing on both sides. Okay. But it's going to be a property that we are going to need. Okay. The other one is the derivative of a norm. Okay, so say I have some vector valued function, and I don't want to use r because we'll be using that later. I don't want it to look like it's the same one as here. So maybe I'll call it q of t. Okay, now we're going to take the norm of q of t. Let's look at the derivative of this. Okay, it turns out that if we take the derivative of this, what we get is q of t dotted with the derivative of q of t all over the norm of q of t. Okay, now this one I will derive for you. All right. So let's let q of t equal to, and I'll just do two components, but the same trick holds for any number of components. Okay, so x of t, y of t. Then with the derivative of the norm of q of t, that means we really want, and this I should have arrows here, these are vector valued functions. Okay, we really want the derivative of, if we calculate the norm, it's the square root of the first component squared plus the second component squared. Right? But that square root, it's just a half power. Right? So if we think about it that way, we can take the derivative fairly easily using a chain rule and the power rule. Okay, so if we take the derivative, we'll need a chain rule. So we're going to deal with the outer power first, leave the inside the same. So take a derivative of the outside, leave the inside unchanged. And then subtract 1 to get your new power. Okay, so far so good. Let me give myself a little more room here. But then we have to do what? We have to multiply by the derivative of the inside. Okay, so the derivative of x of t squared, the derivative of y of t squared with respect to t. Again, we're going to need a chain rule here because it's not just x of t, it's not just y of t, it's x of t squared. It's y of t squared. So let's do a power rule. So I get 2 times x of t to the power of 1 times the derivative of the inside, which would be the derivative of x. Plus, same thing here, power rule, 2 times the derivative of y of t to the power of 1, and then I need to multiply by the derivative of the inside, so the derivative of y of t. Okay. Now let's tidy things up a little bit. First, I could factor this 2 out and cancel it with the 2 down here, right? So those 2's cancel. In my denominator, I have this because of the negative in the power. And the half means it's under a square root. So square root of x of t squared plus y of t squared. Okay? And on top, notice I have something in both of these terms, in both of the products. The left factor are the components of q of t. The right factor are the components of the derivative q prime of t, right? And so we could think about this as a dot product of, let me color code it for you, x of t, y of t, dotted with x prime of t, y prime of t. Okay, and now just plug in what everything is. X of t, y of t, well, that was just the original function, q of t. X prime of t, y prime of t, that's the derivative of q. And square root of x squared plus y squared, that's the norm of q. Which is our result. Okay? All right. So with these two results, let's see if we could derive a different expression for the norm of t prime of t. Okay? So I'm going to start with t, the unit tangent vector t of t. Okay? And I want to take the derivative of that so I could get t prime. Okay? Before I do that, though, remember the unit tangent vector of t, it's just r prime of t divided by the norm of r prime of t. Okay? And to make things simpler, I'm going to leave off the of t, because we're going to deal with a lot of r's and r primes and r double primes. Okay? So just to keep things simple, I'm going to leave off the of t. Notice that it's still there. These are still functions of t. I'm just being a little lazy and making it a little more readable by leaving off the of t part. Okay? So I want the derivative of, let me write it using this notation. I want t prime of t, which is the derivative of r prime over the norm of r prime. Okay? Now this is going to be a quotient rule, right? So the derivative of the top, r double prime, times the bottom unchanged. Minus, now the top is unchanged, and I multiply by the derivative of the bottom, but the derivative is the norm of a function. We just looked at how to take that, didn't we? The derivative of a norm of a function is the function dotted with its derivative over the norm of the original function. Okay? So since my function is r prime, I take the function r prime dotted with its derivative, which would be r double prime, over the norm of the original function, norm of r prime. Okay? And then finish off your quotient rule. All of that is over the denominator squared. All right? Okay. So let's tidy this up a little bit. I don't like the fractions on fractions, that we have a fraction on top of our fraction. So what I'm going to do is I'm going to multiply top and bottom of this by the norm of r prime. On top, if I distribute, I get r double prime times the norm of r prime squared, since I'm multiplying this in, and there's already one there. And then in the second term over here, it'll just cancel when I multiply it in. So I'd get r prime times the dot product of r prime and r double prime. And in the denominator, I get the norm of r prime cubed. Okay? All right, let's do one other thing here. Norm of r prime squared. Remember, the norm of something squared is just the dot product of that something with itself. So r double prime, and instead of norm of r prime squared, I can write it as norm of r r prime dot r prime. Okay. Now, this numerator, it has a form that looks familiar. It looks an awful lot like what we have over here, right? So instead of writing it as this dot product expression, we can rewrite it as a cross product. Okay? So using this triple cross product rule, we would get our numerator becomes, and I need to be careful that I get the order right here. I believe r prime cross r double prime cross r prime over the norm of r prime cubed. Okay? Okay, we're almost done. So this is the the derivative of the unit vector t, right? The unit tangent vector t. We want, though, if we look at our original formula for curvature, we want the norm of that unit tangent vector. Okay? So let's get the norm of the unit tangent vector and see if we could simplify this any further. Okay? So that's going to be the norm of this. So the norm of r prime cross r double prime cross r prime. And since the denominator r prime cubed is just a positive scalar, I could pull it out of the norm, and it could just be sitting by itself. Okay. Now we're going to use one of our properties of the norm of the cross product. The norm of a cross product is the product of the norms of the vectors. So the norm of this vector with the norm of that vector. Times sine of the angle between them. This is a property we learned about when first talking about cross products. Okay. Now we could see that this and this will cancel, leaving me just two norm of r primes on the bottom. But what about this sine of theta? Well, notice that this vector here is the cross product of r double prime and r prime, which means it will be orthogonal to both of these vectors, right? It will meet both those vectors at a 90-degree angle. So this resultant vector is meeting r prime at a 90-degree angle. Theta has to be 90 degrees. It has to be pi over 2. Okay? And sine of pi over 2 is 1. And so I get that the norm of t prime of t is the norm of r double prime cross r prime over the norm of r prime cubed. I'm sorry, squared. Okay? All right. We now have a nice expression for the norm of t prime of t that does not involve any arc length parameters. It also doesn't involve us having to normalize any vectors and take the derivative of that normalized vectors, which really is very unpleasant to do. Okay? So what we want to do now is just plug this back into our equation for curvature, our formula for curvature, which, as a reminder, formula for curvature is the norm of the unit tangent vector t prime of t divided by the norm of r prime of t. And we just found a different expression for the norm of t prime of t. It's this, okay? So if I plug that in, I get the norm of r double prime cross r prime on top. And on bottom, I already have a norm of r prime of t, and I get 2 more. So altogether, I will have norm of r prime of t cubed. Okay, this is the easiest formula that I know of for curvature. That's the one that we will be using to make our life as easy as possible. All right, now that we've done the hard work of deriving the formula for curvature, let's take a look at an example where we actually have to evaluate the curvature. Okay, so just as a reminder, the formula we derived for curvature, the easiest one to use, is the cross product of the first and second derivatives of our parameterization. We take the norm of that and then divide by the norm of r prime of t cubed. Okay, so we just need to take our 2 derivatives, find their cross product, and then do some norms. So I've got r of t here. Let's quickly find r prime of t and r double prime of t. R prime of t is -5, 25t to the 4th, and 8t. All right. R double prime of t is equal to 0, 100t to the cubed, 8. All right. In the numerator, I'm going to need the cross product of these. All right. So here I have it written as r double prime cross r prime. Because I'm taking the norm, it actually doesn't matter the order I do it in, whether I have r double prime first or second, because all that does is changes the result by a sign. And since I'm taking the norm, the magnitude of the two will be the same. So whether you want to calculate r double prime cross r prime or r prime cross r double prime, after taking the norm, you will get the same magnitude. Okay? So let's calculate r double prime of t cross r prime of t. That's going to be the determinant where the first row is ijk. And you know what? I'm making things a little hard on myself. I don't care about the curvature at every single point. I only care about it at a particular point. So instead of plugging in r double prime of t and r prime of t with all those t's, let's first plug 1 in. Now that I'm done with taking derivatives, let's plug in the 1. And then I only have to deal with specific numbers instead of a bunch of variables. Okay? So I care about r prime of 1, which is -5, 25, 8, and r double prime of 1, which is 0, 108. Okay? So let's take the cross product of those. R double prime of 1 cross r prime of 1. So first row ijk. Second row is the first vector. So first goes first. 0, 108. And second. Here I have it written as r prime, -5, 25, 8. Okay, so I get 800 minus 200, that's 600i. And for j, I get 0 minus -40, which is 40j. And k, I get 0 minus -500, so that's going to be 500j, or 500k. Alternate signs, plus, minus, plus, and we have our cross product. All right. I have everything I need. Now I just need the norms of these guys. Okay, so let's kind of plug in. So the curvature at 1, at t equals 1, is going to be the norm of my cross product. So here's my cross product. So let's find the norm. So that's going to be square root of first guy squared plus the second guy squared plus the third guy squared. And I divide that by the norm of r prime cubed. So here's my r prime at 1, negative 5, 25, 8. So I'm going to have square root of negative 5 squared plus 25 squared plus 8 squared. And then I cube it because that denominator is cubed. Okay? Numbers here are awfully big. Okay? This is why we have calculators, right? So let's pull up a calculator. So let's just throw it all in. I have the square root of 600 squared plus negative 40 squared plus 500 squared, and all of that is over the square root of negative 5 squared plus 25 squared plus 8 squared, and still in the denominator. And all of that, all that's under the square root is cubed. And so we get our final answer is 0.0499. That is the curvature. At that exact moment, that exact point. That's how we measure how curvy it is. Okay, not an especially big number, is it? So you would expect that this curve is not especially curvy at that point. Okay, let's take a look. Bring the graph over here. So that blue line there, that's our curve. Okay, and we're interested in when t equals 1. So if you plug 1 in, that's the point negative 5, 5, 4. So if we plot that point, that is where we are measuring the curvature at. And just looking at it, it looks almost flat, doesn't it? It does not look very curvy at all. And so our answer jives with the test of common sense, okay? We look at this and we're like, there's not a whole lot of curvature. And if we look at our answer here, this is a small number, so we would not expect a lot of curvature.